Far from Earth, this unit, equal to about 150 million kilometers, is the usual measuring stick for distances in our solar system. Consider this: light, traveling at an astounding pace of 300,000 kilometers per second, takes approximately 8 minutes and 20 seconds to journey from the Sun to Earth. If you were to travel this distance in a commercial jet flying at 900 kilometers per hour, it would take you approximately 19 years. This vast distance is a stark reminder of the vastness of space, even within our own solar system. The Sun, a fiery behemoth, provides life-sustaining energy to our planet from this incredible distance. Venturing beyond our home planet and its solar companion, the Sun, we set our sights on Mars, our enigmatic red neighbor. Mars, at its closest approach to Earth, is about 54.6 million kilometers away. But this distance can stretch up to 401 million kilometers when the two planets are on opposite sides of the Sun. To put that in perspective, traveling to Mars at the speed of a commercial jet would take upwards of 50 years. This vast expanse of space between Earth and Mars has been a significant challenge for space exploration. The rovers and probes we've sent to the Red Planet embark on a journey that is not just far but fraught with complexities due to the constantly changing distances and orbital dynamics. As we journey to the outermost reaches of our solar system, we encounter Neptune, the remote ice giant lying roughly 4.5 billion kilometers from Earth. Neptune marks the brink of our solar neighborhood. Sunlight racing across the vacuum of space takes approximately 4 hours and 15 minutes to reach Neptune from the Sun. This impressive distance showcases the enormity of our solar system. Launched in 1977, the Voyager 1 space probe represents humanity's insatiable curiosity and our desire to explore beyond known boundaries. As of now, Voyager 1 has traveled for over 4 decades, covering a remarkable distance of more than 22 billion kilometers from Earth. It is the farthest human-made object from our planet, a silent wanderer in the cosmic sea. In 1990, at the suggestion of the renowned astronomer Carl Sagan, Voyager 1 turned its camera back towards Earth for one final image. This resulted in the iconic pale blue dot photograph. At a distance of about 6 billion kilometers from Earth, our planet appeared as a tiny faint dot in the vastness of space. Sagan poetically reflected on this photo, emphasizing our responsibility to cherish and preserve our only home, a small speck in the vast universe. At the very fringes of our solar system lies the Oort Cloud, a vast theoretical sphere of icy objects. This remote cloud is thought to extend up to a staggering 100,000 astronomical units from the Sun. That's approximately 1.9 light-years, a distance so vast that it is at the cusp of interstellar space. Scientists determine the boundary of interstellar space, known as the heliopause, where the Sun's solar wind is stopped by the interstellar medium. This is where the influence of our Sun ceases, and the vast realm of interstellar space begins. The Oort Cloud represents the final frontier of our solar system, a boundary region where the Sun's influence wanes, and the cosmic journey into the galaxy truly begins. As we venture beyond the confines of our solar system, our next point of interest is Alpha Centauri, the closest star system to our Sun, located about 41.3 trillion kilometers away. This distance is equivalent to over 276,000 astronomical units. At such vast distances, the AU, a measure so convenient within our solar system, begins to lose its practicality. As a result, astronomers use the light year, the distance light travels in 1 year, for interstellar measurements. Alpha Centauri is about 4.4 light-years away from us. Considering our current space travel technology, a journey to Alpha Centauri is almost unfathomable. For example, the Voyager spacecraft, traveling at approximately 17 kilometers per second, would take over 70,000 years to reach this neighboring star system. This immense distance underscores the vastness of space that separates the stars and highlights the challenges of interstellar travel. Our journey now takes us to the grand scale of our home galaxy, the Milky Way. Spanning about 100,000 light-years in diameter, this vast spiral galaxy is home to hundreds of billions of stars, each potentially hosting their own planetary systems. Within this immense structure, there is a tiny sphere known as the human radio bubble, extending about 100 light-years from Earth. This bubble represents the farthest extent of human influence within the cosmos, the reach of our radio and television broadcasts into space. Beyond this bubble, it's as if humanity never existed. Any civilizations living in the vast majority of our galaxy would be oblivious to our presence since our signals haven't reached them yet. The scale of the Milky Way is so vast that our entire recorded history is but a whisper in the cosmic wind, undetectable beyond this small bubble. As we leave the Milky Way, we enter the vast, almost incomprehensible realm of intergalactic space. Here, galaxies drift in the cosmic ocean, separated by mind-boggling distances. Our galaxy is part of a small cosmic community known as the Local Group, a cluster of more than 50 galaxies spread across approximately 10 million light-years. The Local Group is a diverse assembly, including not just spiral galaxies like the Milky Way and Andromeda but also a multitude of smaller dwarf galaxies. The distances here are so vast that light from one end of the Local Group to the other would take 10 million years to traverse. This scale dwarfs anything within our own galaxy, underscoring the enormity of the universe. Intergalactic space is a silent expanse, a vast wasteland between the islands of galactic light. In this immense void, our galaxy, home to our entire history, is just a tiny speck among many, a single story within the grand cosmic library. As we expand our cosmic gaze beyond the Local Group, we encounter the vast Virgo supercluster, a tremendous collection of galaxy groups and clusters, including our own Local Group. Encompassing an area of space about 110 million light-years in diameter or 33 megaparsecs, the Virgo supercluster is a massive structure in the universe, containing thousands of galaxies from at least 100 galaxy groups and clusters, each with their own myriad stars and planets. As we journey outward from the Virgo supercluster, we arrive at an even more awe-inspiring cosmic structure, the Laniakea supercluster. This colossal congregation of galaxies, which includes the Virgo supercluster, extends over 500 million light-years. It is our galactic home on a grand scale. Laniakea, meaning immense heaven in Hawaiian, truly lives up to its name, containing the mass of 100 million billion suns. Laniakea is a gravitational masterpiece, with galaxy clusters, superclusters, and countless celestial bodies bound in a cosmic web of attraction and motion. At the heart of Laniakea lies the Great Attractor, a mysterious region of space that exerts a massive gravitational pull on the galaxies within this supercluster. In this vast expanse, our Milky Way, the entire Local Group, and even the Virgo supercluster are just tiny components of this massive structure. Laniakea provides a profound context for our existence. In this titanic supercluster, we are part of something far greater and more majestic than we can fully comprehend. JWST, set to launch in the coming years, is designed to observe in the infrared spectrum, allowing it to peer through cosmic dust and reveal the formation of stars and galaxies in the early universe. Its advanced instruments will provide new insights into the atmospheres of exoplanets, potentially identifying signs of habitability or even life beyond our solar system. The data from JWST will complement observations from other telescopes, such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the upcoming Extremely Large Telescope, ELT, creating a comprehensive picture of the universe's history and evolution. The exploration of space is not limited to telescopes and robotic missions. Human spaceflight remains a crucial aspect of our quest to understand the cosmos. The International Space Station, ISS, a collaborative effort involving multiple space agencies, serves as a platform for scientific research and international cooperation. Astronauts aboard the ISS conduct experiments in microgravity, study the effects of long-duration spaceflight on the human body, and test technologies essential for future deep space missions. Looking ahead, plans for human missions to Mars and beyond are taking shape. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, establishing a sustainable presence and preparing for future missions to Mars. Private companies, such as SpaceX, are also developing ambitious plans for interplanetary travel. SpaceX's Starship spacecraft is designed to transport large numbers of people and cargo to Mars, with the ultimate goal of establishing a self-sustaining human settlement on the Red Planet. The challenges of interplanetary travel are immense, from the technical hurdles of spacecraft design to the physiological and psychological effects of long-duration spaceflight. Radiation exposure, microgravity-induced muscle and bone loss, and the isolation of space travel are significant concerns that must be addressed. Advances in medical research, life support systems, and habitat design are essential for ensuring the safety and well-being of astronauts on these long journeys. As we continue to explore and understand the universe, the importance of international collaboration and the sharing of knowledge cannot be overstated. The global community of scientists, engineers, and explorers must work together to overcome the challenges of space exploration and make the most of the opportunities it presents. Initiatives such as the International Space Exploration Coordination Group, ISEC, and the Global Exploration Roadmap exemplify the collaborative efforts needed to achieve our ambitious goals in space.